All right, last example from the notes for the entire year. New stuff. We are talking about Lagrange error bound, also known as Taylor's polynomial error. This one was the actual question on the 2011 exam. It was the last question, which is typically the sequences in series. Let f equal sine of x squared plus cosine of x. Okay, will do. The graph of the absolute value of the fifth derivative of that function f is shown at right. There it is. Okay, cool. Write the first four non-zero terms of the Taylor series for sine of x centered at 0. And then write the first four non-zero terms of the Taylor series for sine of x squared at 0. So they're kind of walking you through what eventually is going to be you creating that function, right? But they're doing it in little baby steps. They want to give you points. They want to, okay? So first of all, it's a series, so is it going to be equals or squiggles? Equals, right? And we're writing the first four non-zero terms. Does it say to write the nth term or the general term? No, so don't volunteer it if they didn't ask for it. So here we go. It's centered at 0, so it's really the Maclaurin series. It's the one we memorized. So sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Is that the first four non-zero terms? Nope, need one more. Minus x to the 7th over 7 factorial. And because it's a series, I have to say plus dot, dot, dot. If it were a polynomial, I would have a squiggles, and then I'd stop. Okay. That looks good. And now I'll do the same thing for sine of x squared. So right below there, we'll build it. And this is substitution, right? So we'll just replace x with x squared. And we get x squared minus x to the, it's probably easy just to simplify as we go. X squared cubed is x to the 6 over 3 factorial. Plus x squared to the 5th is x to the 10th over 5 factorial. Minus x squared to the 7th is 14th over 7 factorial plus dot, dot, dot. All right. Is that all they asked us to do on part A? That was pretty easy. Maybe that's 8 points out of 9, huh? Hopefully. Yeah, probably not. Sweet. Okay. Man, what a graph. I can't keep my mind off it. All right. I wonder if we're going to be using it for something later. Okay. B. Write the first four non-zero terms of the Taylor series again for cosine centered at 0. And then use the series for sine of x squared found in part A. I remember that. To write the first four non-zero terms of the Taylor series for f. It's just like building this function, right? So here we go with cosine. It's a series. So cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th. Oops. There we go. Over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. So notice if you didn't have these memorized, you'd be busy off to the side like a little beaver generating the numerators of the coefficients by using Taylor's derivative theorem or whatever it's called, right? So time saver to memorize these. Memorize them if you haven't already. Okay, and now it says to use what's in part A to write it for f of x. So here we go. F of x is going to equal, it's going to be, if you come up here, it's the sine of x squared plus the cosine. So on the AP exam, you'll just have to physically rewrite it. But here I can copy it. Like that. And then I can paste it. Actually, let me get rid of this f of x first. Because if I just paste the cosine one on the back end of it, that would be okay, plus dot, 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 plus dot, dot, dot. But in this case, if I leave the f of x off, I could actually do this, and I can write it underneath that one. And then I can add them together, right? Like this, somehow. Now, would I need to do that, or could I just put them one behind the other? I could probably put them one behind the other. Yeah, as long as it's plus dot, 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 and then the other one plus dot, dot, dot. But let's see what we get here when we we add them vertically. Let me come over here. We can start adding like terms. So I have a 1, and then I got some x squareds, right? So those are like terms. So that's going to be a plus. I'm going to factor the x squared out. So the coefficients are going to be 1 minus 1 over 2 factorial times x squared. And then I don't have an x to the 4th in both of them, so it's just x to the 4th over 4 factorial. And then I've got some x to the 6s. I'm not even sure if I like doing this. You think it's going to be worth it? I don't think it's going to be worth it. I thought maybe that somehow they would combine to give us something kind of cool. So anyway, I thought about it. We abandoned that thought, and we'll just go straight to answering the question. Okay, good try, me. F of x equals, and then it's the sign one. So I forgot what I copied last. Let's come back here and do this again. It's that one. Paste. And then it's plus dot dot dot, and then I'll put plus, and then this one here at the back end of that. Copy. Paste. Plus that, plus dot dot dot. So there you go. Not the best ordering, but it works, right? If they wanted you to add those together, they would probably say something like show that the series equals this. And that would give you like the cleaned up version of it. And then you would have to show that you're adding them and getting that result. But it didn't do that. It just says to write the first, oh, hang on, back up. There was a part. I knew there was something I was missing. Write the first 4 non-zero terms of the Taylor series. That's where they're going to get you. Write the first 4 non-zero terms. Did I do that? Technically, yes, right? Are they all there? Let's see if I can start writing them in order. All right, what would be the first term? 1. And then the next term, let's just write them side by side, plus x squared minus x squared over 2 factorial. That would technically be the second term. And then the third term, what would be the next power? X to the 4th, and there's only one of them, x to the 4th over 4 factorial. So that'd be 1, 2, that's 3 terms. And then the 4th term would be the x to the 6s, and they're both negative, right? So minus x to the 6 over 3 factorial minus x to the 6 over 6 factorial, and then plus dot, dot, dot. Okay, so I will go ahead and kind of clean it up. So I did have an x to the 14th there. I didn't write them in order. You're going to want to write them in order, okay? Now let's do one last thing. Since it looks like it's more than 4 terms, we'll say 1 plus, and I'll just factor out the coefficients. We don't necessarily have to combine them. Oops, kind of getting cramped in there. 1 minus 1 over 2 factorial is that, times x squared, factor it out on the right, plus x to the 4th over 4 factorial, and then minus, we'll do this one 2 different ways. I'll factor out negative, and then I'm left with positive 1 over 3 factorial plus 1 over 6 factorial times x to the 6th plus dot, dot, dot. There we go. Okay, so careful reading goes a long way. It's not the manly thing to do, right? Reading the instructions. When all else fails, read the instructions. Okay, so how does that look? 1, 2, 3, 4. Cool. All right, cool. I'll leave it at that. So yeah, you might want to, before you walk away from a part, just go kind of back and reread carefully and make sure you've answered everything, because they could, maybe you missed the general term, or maybe you added the general term and it didn't ask for it, you go back and erase it. In this case here, if I leave the minus x to the 14th over 7 factorial, is that okay? If I leave it, since it wasn't one of my first 4 terms? I can, but it has to be right, yeah? So that you might want to go back and erase that, so on and so forth. Okay, so here we go. Find the value of this. Find the value of that. Any idea how we're going to do that? Derivative? Well, that would be the 6th derivative. Do you want to take, if I generated f of x up here, do you want to take the derivative of that 6 times? No, that would take a while. So here's this type of question, and we've done it already. You're going to use Taylor's theorem here. You're going to use Taylor's theorem. There are two ways now to get this answer. One from the polynomial we generated and one from Taylor's theorem. So remember, the coefficient of the x to the sixth term from Taylor's theorem is the sixth derivative evaluated at the center, which is 0, over 6 factorial, right? That's how we generate all the coefficients for any degree n, right? In general, let me write it up here. It's the nth derivative at the center over n factorial. These are the coefficients from Taylor's theorem. Now, do we have another coefficient for the sixth degree term somewhere? This right here. That is the coefficient of the sixth degree term, is it not? It is. So those two should be what? They should be equal to each other. Yeah. So here we'll go over here and we'll say then that the sixth derivative at the center 0 over 6 factorial is equal to, and this is where you got to be careful. I factored out the negative, 1 over 3 factorial plus 1 over 6 factorial. Boom. Very typical. Most people are going to forget to divide by 6 factorial on the left in Taylor's theorem. And a lot of people just take, boom, the coefficient of the polynomial. But now we just have to solve for this numerator, right? And all we have to do to solve for the numerator is multiply both sides by 6 factorial. So it's the sixth derivative at 0 equals negative 6 factorial times 1 over 3 factorial plus 1 over 6 factorial. How's that for an answer? A little messy, but it's good. It's exact. Yeah, that's good. Now that would be the same answer you would get if you did take the derivative 6 times of the polynomial and plug in a 0. Well, no, we don't want the x because remember it was just asking us for the sixth derivative at 0. So we just work with the coefficients, okay? This is a hugely important type of question. Any comments or questions on that? Compare two different coefficients, the one from Taylor's theorem and the one from the polynomial or the series polynomial generated. All right, for kicks and giggles, I'm just kind of curious what this simplifies to, yeah? If I distribute the negative 6 factorial, that's negative 6 factorial all over 3 factorial minus 6 factorial over 6 factorial. And I would not do this on an actual exam, but I'm kind of curious if it simplifies down to something cute. All right, negative 6 factorial over 3 factorial. That's the same as negative 6 times 5 times 4 times 3 factorial, yeah? And so what happens with your 3 factorials? See ya, wouldn't want to be ya. Minus 1. So that ends up being, ooh, that's a big number. 6 times 5, 20 times 6 is 120. So negative 120 minus 1, it ends up being negative 121. That's the value of the sixth derivative at 0. How many bonus points do we get for calling it negative 121 versus calling it this? 0. Okay, 0. Yeah, probably minus 1 because there's a chance you messed up. Yeah. All right. So far, so good so far? Okay. So here's the last part. Let P sub 4 of x be the fourth degree Taylor polynomial. So again, we use M for Maclaurin, usually T for Taylor, in this case generically P. But it is a Maclaurin series, and the subscript, remember, is the degree, not the number of terms. Let it be the polynomial that approximated centered at 0. Using information from the graph of that, which was now shown above and not at the right, I was thinking about the graph. Show that this is less than 1 over 3,000. So as we've been going through this section, I've been writing the error many, many, many different ways so that you would be accustomed to however they do that. So let's go ahead and write it out. This right here is really the error. That's a generic term. We also call that the remainder when we use the fourth degree polynomial evaluated at x equals 1/4. All right, so that's another way to write it. And of course, I'm just going to rewrite this. This is p sub 4 of a fourth, which is your approximate value, minus f of 1/4, which is the actual value. And you take the absolute value. So those could be switched. They could give you that. So we want to show that that's less than 1/3000. So is this Lagrange error bound? Yeah, essentially anytime you have a polynomial and you're looking for error, it's Lagrange error bound. Now, in the case that it's an alternating series, you can actually use the alternating series test, which remember says that the error is going to be less than the absolute value of the first unused term at that value of x. But I'm not sure if this one alternates or not. Maybe it does. Yeah, maybe. Let's just go ahead and use the Taylor's theorem or Lagrange error bound. So I know that this is going to equal, from the theorem, it's going to equal, let's see, if I use a fourth degree polynomial, that's n equals 4, then I have to look at one larger than that, right? So I need to look at the fifth derivative, evaluated at some magical number z, all over 5 factorial times x minus the center to the fifth. What's the x value we're approximating it at? 1/4. And what's our center? 0. So again, there's me just writing it. That's Taylor's theorem. Now again, we're never going to be finding z. Okay, we don't know what z is. So what we're going to do is we're going to find the maximum of the absolute value of the fifth derivative on the interval between the center and x. So that would be on the interval between 0 and 1/4. On the interval between 0 and 1/4. That's what this comes down to. And of course, we already knew from the sine and e that if we can't find a true maximum on that interval, we will go up, not down, we will go up to the first available easy number. We want to keep it as small as possible, but we also want to make it easy, right? Bless you. So where are we going to get that information? The graph, right? And some of the problems they handed to you. But now we're going to go to the graph, and we're looking from 0 to 1/4. So they gave us more graph than we needed. It's always between the 0, or the center, which in this case is 0, and 1/4. Hey, look how they partitioned it. Did you notice that? 1 is over there, so 1/4 is right here. It's like they were trying to help me. There's 1/4. Okay? So what I truly, truly want is the maximum value on that interval, which, of course, if you look at it, it's the right endpoint. But what is that value? Do we know for sure? No. It's going to be more than, let's see, they're counting by 20s on the y-axis. I can't just assume it's halfway between 20 and 40. I can't call it 30, can I? Because I don't know if it's 30. It's not marked. It could be, it could be 28, could be 31. So what's the first number that's safe to use? 40. There you go. Everyone see that? They're trying to guide you to 40. It's the first number that we know for sure that is bigger than the maximum value on that interval. So we got 40. And of course, we could have used, 80? We could have used 120, but that defeats the purpose of what we're trying to do. So what we'll do now, and notice it's still an equal sign here, when I replace that with its maximum value, that's where the inequality comes in. So this now becomes 40 over 5 factorial, and we simplify. I'm going to get rid of this. There we go. We simplify times 1/4 to the 5th power. Okay, and now we have to show that that number is less than what? 1/3000. And when it says to show, see when it says to show, that means you actually kind of need to do a little bit of work. Don't just do this. Okay? Don't just do that. That's kind of taking it on faith. It should be, but you haven't showed it. Shown it. Shown it, have shown, shown, participle. Okay. So I'm going to work down here just because I have more room. 1/4 to the 5th power is the same as 1/4 to the 5th. And let's see. That's 40 times 1. I'll just 40. And then 5 factorial, that's 5 times 4 times 3 times 2 times 1 times 4 to the 5th is 4 times 4 times 4 times 4. Why do I want to do that? I have no idea. 40 divides out with 5 to give me 8. Oh, 1, 2, 3, 4. Yeah, there was another one. Okay, 5. Okay, there we go. 8 divides out with this 4 to give me 2. That 2 divides out with this 2 to give me 1. So this now is equal to 1 over 3 times, and I guess I have to start multiplying these two together, or these, what are left together. So it's going to be a 16 times a 4 times a 4 times a 4. Oh, wrap around. Okay. That's 3 times 16 times 4 is 64 times there's 2 4s left. Again, you can do this in any way. I'm just kind of having fun right now. 64 times 4, that's going to be 256 times 1 more 4. So I'm trying to keep it from doing 2-digit multiplication here, because that's going to require like old stacked multiplication. I don't want to do that. So 256 times 4. Whoa! Okay. And then over here, one more time, we're going to get 12,703. Is that right? I think so. And now, that is less than 1 over 3,000. Yeah, very good. And we know now for sure that it is. Okay? So be careful when they say show. It's more than just like pointing arrows. You know? We actually have to do the work. Do you understand Lagrange error bound? Okay. What's important is that it's the first unused value of n. Like the alternating series is the first unused term, which is kind of the same thing. But for Taylor in general, it's the same form, right? It's the nth derivative over n factorial. The only difference is instead of keeping it as an x minus the center, we're evaluating it at a specific x. So we plug it in, and then we find the maximum value of the first nth, or the n plus first derivative on the interval. And that's what's important. It's on the interval between the center and the value of x we're using. If we would not have used that interval here, if I would have just found the maximum value on a different interval, I might use the local maximum here and say I'm going to use 60, which would not be as good as we can get it. Or if I looked at the entire graph, I might say, oh, okay, I'm going to use 140, whatever, okay? Okay, if you go too far out, then that's good. If you go too far out, good point, Colin. If you go too far out, then this number here, which is in the numerator, is going to make your error bigger, which is going to make this fall short of your target. Yeah, so it's kind of built into the system. Yeah, all right. You want to keep it as small as possible, but guaranteed that it's going to fit in there, right? So you never go smaller, you always go bigger to the next comfortable value. Good point. Colin's on fire today, everybody. Okay. I hope we don't have a fire drill. We don't want to put it out. Okay. There you go. Comments or questions then? All right. Well, we'll stop right there then. That's it. That's BC Calculus. Well done.